Welcome to the Insightful Professor. Today we continue our examination of using arrays in the Java language. Specifically, we're going to talk about how to access the elements that are stored in an array. Recall that last time we talked about how an array was created, how it's declared within a program, talked about some of the concepts of the structure and the organization of the elements. Today we'll talk about how to access the elements. That will include discussing how to store values within the elements, as well as how to retrieve those stored values. So when accessing any element of the array, the variable name is the same. That was the selling point of why we want an array. What we do is we declare an array and we have what's called a reference variable, because recall that an array is actually implemented in Java as an object. So this reference variable will be used throughout all access to the elements of the array. Regardless of which element we're going to access, we use the same variable name. The thing that is different is that we will provide an index or a subscript value, and that's what will distinguish one element, and hence its value, from another element and its value. When working with an array, we typically access all of the elements within the array. To do this systematically, we tend to use a loop, and in particular we use a for loop, because what we're going to do is change the value of the subscript or the index. So it's a count-based loop, hence a for loop. In this example, we use an integer declared within the for loop called I. This will assume the values of the subscript or index for the array. Remember, it's a zero-based kind of counting scheme for the index or the subscript, so therefore we initialize I to 0. Then we stay within the bounds of the array. Remember, the array being zero-based, if it has 10 elements, the highest subscript that will be valid will only be 9. It'll be one less than the length. So therefore, we put a relational operator here. So as long as I, this variable that represents the subscript, has a value that is less than the number of elements, less than 10 in this case, will go into the body of the loop and process another element. To ensure that we do process another element, our for loop includes an increment at the end of the loop. Increase the value of the subscript by 1. So here we're accessing int array, that's our reference variable, and I is our subscript. And all we're doing in this case is assigning a value to 0. But the point is we're iterating through the collection of elements, and we're looking at these one by one. Let's take a look at this in the actual program called ArrayDeclaration1.java. At the top of the program, we declare a named constant identifier, so a named constant. Here we call it size, and its value is 10. This is going to be used to impose a limit on the number of elements within our declared array. So on line 14, we actually proceed to declare that array, and we invoke the constructor to bring the object into existence, saying create an array of integers of 10 elements. Then we have a work variable here that will be used to hold the values of the index or the subscript as we work our way through the elements. And here's the loop that we had looked at just a moment ago. So we use the identifier size rather than hard coding a literal value of 10. And here we work our way through the loop one by one. So what we did was we obtained the element here and simply sent it to the console for display. Down here, we're doing it in 2 steps, just to show you that you can do additional work. This allows us to retrieve the value of the element and then use it in additional operations within the body of the loop. So let's fire this up and see exactly what happens. Okay, not very exciting because all of the values in the array happen to be 0. So as we go through and look at this, we see all the zeros listed. Not very revealing. And likewise, in the other case, it was the same result. But the point that I wanted to get across with the example was we could systematically examine or access each element within the array by using the for loop and using a variable that identifies the element position or the subscript. Let's return to our presentation and continue our discussion. In the example that was just presented, we noted that all the elements were accessed using the same name, the name of the reference variable. The index or subscript value was placed within the square brackets adjacent to the name of the reference variable. And this is how we distinguished one element from another, by changing the value of that index or subscript. In using this syntax, we have three options for identifying the element position. We could provide a literal value within the square brackets. We could use the name of a variable, or we could formulate an expression which will first be evaluated to determine what the integer position is, and then access the element that occupies that particular position within the array. But in each case, the value within the brackets must map to a specific element position. That is, it has to evaluate to a subscript for the array, which means it has to be an integer. We want to introduce one additional point with the declaration of an array. We had looked at declaring an array by saying we're going to define a reference variable and specify the base type, what kind of values will be stored within the array. Then we indicated to bring the array into existence, we effectively invoke the constructor by executing the Java new operator. That causes the memory to be allocated, the address of that memory to be determined, and stored back in the reference variable. So we said we could consolidate those operations into a single statement. But there's even one more thing that we can do. Instead of just initializing the elements to their default value, whatever that is for the base type of the array, we could actually assign the values within the declaration statement. This is accomplished through what's called an initialization list. This is not unique to Java. You'll see this in other languages such as C++. So it's an important concept to understand. So the way we do it is we again announce a base type for the array, specify the reference variable that will be used to access the elements of the array. Then we have the assignment operator, but instead of being assigned the address that results from invoking the new operator, what we're going to do is actually list the values that are going to be stored within the elements. This is referred to as the initialization list. When we use an initialization list, there's an interesting thing that happens. We first off do not explicitly state the size. We don't say how many elements are going to be present within the array. That length or size is determined by the compiler as it examines the number of elements stored within that initialization list. So it would count the values, say in this example, and see that there are 3 elements, and assign the length value a setting of 3. So that's one syntactic difference. Also note we do not actually use the new operator. That kind of is implied as happening by using the initialization list as part of the assignment. This technique of using an initialization list is useful when you have a relatively small number of element values to be placed within the array, because you're identifying all of the values right here within the state. For large numbers of elements, this may not be so practical. So when the array is declared and initialized with an initialization list, the following things actually happen. What happens is the reference variable is declared, an array is actually created, or the array object is instantiated in memory, and the value of that array location, that address, is placed within the reference variable, and then the values within the initialization list are stored within consecutive elements, starting with subscript 0 and then moving forward. So in our example, we had 3 values of 2, 12, and 1 listed in that order. So value 2 goes into the array subscript 0, value 12 goes into the array subscript 1, and value 1 into the array subscript 2. Let's take a look at this guy in action with the program arraydeclaration2.java. Near the top of the program, the array is declared with the initialization list. We then have our variable that will be used to identify the index or subscript values as we perform selection to specify a particular element. And here's our simple array to process the elements. Notice that we're using 5, we're hard coding that. The reason for 5 is that's the number of elements that appeared within the list. Now this is a little tricky because that means I would have to know up front, okay, 10, 20, 30, 40, 50, there are 5 elements. And I have to know that when I provide the value in here. So we'll look at a better way to achieve this in just a moment. But again, it's the same mechanism for working through the elements, for iterating through the list of elements. We simply use a for loop and go from 0 up to 1 shy of the number of elements within the list. And it works exactly the same whether we declare the array in the traditional manner that we described earlier or whether we use the initialization list. There are the values. This is the result of working through the array with this loop, and we have the element in position 0, position 1, 2, 3, 4. So there's no difference in the functionality when we're using an initialization list. It's just simply a matter of declaring it, bringing it into existence in a different way. So it gives us some flexibility and perhaps some convenience when working with an array that has a small number of elements. When working with an array, we have to be aware of the range of subscript values. Remember that when an array is created, the size of the array or the length of the array is specified. The range of valid subscripts will be 0 up to whatever that size is minus 1. For example, if we have an array of 10 elements, we'll have subscripts that range from 0 to 9. Any attempt to refer to something outside of that range is going to result in an error when the application is run. So it's a runtime error or runtime exception. An array of 10 elements has indices that range from 0 to 9. If we use any value outside of that range, we're going to run into an error. So a common problem that occurs is called an off by 1 error. If we realize that we have 10 elements and assume that 10 is the index or subscript of the 10th element, that's going to cause a problem. Furthermore, if we assume that we have 10 elements and the first one is numbered 1 rather than 0, and access that, we're going to be off by 1. So these are the two types of problems we run into. The off by 1 error where we kind of go beyond what the permitted subscript range is, that results in a runtime error, an exception being thrown. The other error would be starting with 1 rather than 0 as the initial subscript, and we process all of the elements within the array except for the very first one, which has an index or subscript value of 0. Again, we're off by 1 in terms of the calculation of the index or the subscript. Let's take a look at this in a program called ArrayOffByOne.java. In this program, we again work with an array of size 10, where we've declared the size explicitly using a named constant identifier. We declare our array of integers, that's our base type, and we're going to have 10 elements. So if we process all of the elements in the array, and we do this properly, the index will range from 0 up to 1 less than the size. So as long as we're less than the size, we're going to stay within the confines of the bounds of the array. So this works fine. But let's suppose, for example, that we say, oh, the first element, oh, that's element number 1, and we choose to use 1 as the index or subscript for the first element. We properly stop before going beyond the upper bound, but we started within the lower bound, so we missed the very first element, which is actually index subscript 0. So that's an off by 1 error. This is a logic error. The program will not terminate with an error by doing this, but we haven't properly processed all of the elements. The other situation arises when we start at 0 and we go beyond the upper bound by including the size of the array. Remember, the size of the array says the number of elements, but that size never maps to an actual index value. So this would go from 0 through 10, when in reality we have 0 through 9. We would process all of the 10 elements, 0 through 9, and then attempt to go for element with a subscript of 10, which does not exist. It's outside of the bounds. This causes an off by 1 error, which results in an exception, a runtime error. The program terminates with an error. Let's show you exactly what I mean. So in the first case, we have this array here, and we process 0 through 9, and everything works properly. Then we look for the second array, and here's an off by 1 error where we started with the second element, not the first. And when we look at this in the output, we see elements 1 through 9. There's no error. The program processes this properly, except we skipped an element. We missed the first one, which had the index or subscript of 0. And then finally, the third situation. And this is the one that actually results in an error occurring at runtime. That is not a logic error, but a runtime error, causing the program to terminate abnormally. Here we look at the output and we have 0 through 9, which is correct. But when an attempt is made to access element number 10, subscript 10, what happens is we get an error. And the error is pinpointed right here at this line. This is where we refer to the reference variable with a subscript value, but that subscript value happens to be out of range. So the exception is called array index out of bounds exception, and the program terminates right then and there because this is an unhandled exception in this particular application. We did not do this within the confines of a try-catch block. So those are examples of off by 1. Off by 1 could result in a logic error where you don't process all of the data, or off by 1 results in an exception being thrown. The array off by 1 application presented some of the problems that occur if we don't give attention to staying within the bounds of the array subscript. So how do we know what that size is? When we declare an array, we can specify its size and later use that size to control the loop processing so that we access each one of the elements, don't miss any, but don't go beyond the bounds of the array. We saw that in a couple of examples. We also presented the idea that we could have an initialization list, but in such a case, there is no explicit size specified. We don't specify it even as part of the declaration of the array. So how could we use the size of the array if we don't know what it is? That is, if we don't have the value presented exactly within the program. Well, the answer to that comes from something called an instance variable, and this instance variable that we're interested in here is called length. Length is created for each array object that's instantiated, and it doesn't require that the array be instantiated using an actual explicit size. It could be instantiated from the result of an initialization list. So the point is, length is an instance variable that's available with any array that gets instantiated, regardless of the syntax that was used to bring that thing into existence. So the variable contains the number of elements that are within the array. It gets populated when the array object is created. And it is declared as final. By declaring it as final, what happens is we cannot alter it. What this means is an array is a static declaration. So once the array comes into existence, the number of elements is fixed in size. That array cannot grow. So if the array is instantiated with 5 elements, that's all you have to work with is 5. If the array is instantiated with 10, that's all you have to work with. The array cannot grow. The way we refer to this instance variable is by using the reference variable for the array, for example, int array, the dot operator, and then length. So the int array has this field called length, and this is how we make a reference to that field and examine its value. Because int array is an integer, we can use it in an expression. So if we were to say int array.length -1, this would give us the value of the last valid index or subscript. Take a look at the application called Array Declaration 3, which demonstrates the use of this length variable. In this application, we've declared the array using an initialization list. So there is no explicit size. When we go down to the loop to process the elements of the array, what we see is we can refer to the array name and then qualify the length attribute with that array name. So intarray.length is referring to the length variable contained within the int array object, or the object referenced by int array. So what we have is a for loop that starts at 0 and goes just shy of the length, less than the length of the array. This piece of code could effectively be used to process the data in any array. It doesn't matter whether the array contains 5 elements, 10 elements, 1,000 elements. It's going to be determined at runtime by examining the length member variable for the int array object, or the object referenced by int array, examining that value and using that to control the number of iterations. Okay, it tells us the array contains 5 elements. Where did this message come from? Well, right up here, we referred to int array.length as we constructed the message. So it said the value is 5. Then that value of 5 obviously was used down here to control the number of iterations through the loop. And that's where we see the 5 elements within the array being displayed. So if we were to change the size of the array, and I'll do that very quickly here, by going up to the array declaration and adding a couple more elements. Then we compile and run the code. And now what happens is when we run it, it executes and it says, hey, there are 7 elements. And it shows me all 7. What happened here is when the array was allocated, this length variable was created within the array object and assigned a value based upon the number of elements allocated to that array. So when I create the array with 7 elements, length gets set to 7, and then I can refer to that in any particular block of code where I want to process all of the elements within the array. Let me show you one other interesting thing about this. I have some code down here at the bottom that I've commented out, and here is an array reference variable. Array2 refers to or references an array of integer. But this is only a reference variable. It's not pointing to any array, so this is initialized to null. What happens down here is when I go ahead and say, let's look at array2.length, I get an error. What it's telling me is that array2 may not have been initialized. Well, that's true, it hasn't been initialized. The implication to this when following the array2 reference variable is when I go to look for the object, I'm not pointing to an object, so obviously there's no length that I can resolve the reference to. Length doesn't exist. So the point is that the object has to be instantiated in order for the length variable to come into existence, and only then is it valid to make a reference to that member variable. Well, we've looked at how to process the elements of the array, that is, how to access every element within the array using a traditional for loop. But Java has an enhanced version of the for loop specifically for processing the elements of an array. This is also something found in other languages such as C++, so once again, this is an important concept to understand. This enhanced for loop is referred to as a for each loop. The idea being that the loop will process or iterate through each of the elements within the array. The idea being that for each element, we will access that element and process the element according to the instructions within the body of the loop. So how is this implemented? The way it's implemented is we would say for, and then we define a variable which is of the same data type as the base type of the array. Then a colon, and then the name of the array. Following that would be the statement or statements that constitute the body of the loop that are going to do the actual processing of the element value. No reference is made within this structure to the index. That's kind of implied, hidden somehow behind the scenes. So this is thought to simplify the code for people working with arrays. They don't have to get bogged down with thinking about the array position. We just say we want to process all of the elements. For each element in the array, do what the body says to do. So here we have a simple array of 3 integers. Observe that the base type of the array is int. Therefore, this variable that we put within the for loop must be the same as the base type. This data type of int is not because it's an integer for the subscript, but it's an integer because that's the type of thing stored in the array. That's the base type. Then the array is numbers. That's the name of the array here. And finally, we get within the body and we make a reference to val. Val, once again, is the element that will contain a particular value from the array, and each iteration of the loop is going to give us the next value. So we have a little application here called array for each. Let's take a look at that in action to see exactly how this works. We again use the initialization list to declare our array. And what we're going to do is walk through the elements within the array, extract the values, and add them to an accumulator, which we've dubbed here total. So we again refer to how many elements are in the array by using the length instance variable. And here is our little loop. For element, which is of type integer, same data type as the base type of the array. Then the name of the array is int array. We simply refer to element. And as we go through this loop, we will obtain the values of 10, then 20, then 30, then 40, then 50. We'll obtain the elements in the order in which they reside within the array. The second version of this loop is a little bit more involved. We can use an element data type that's the same as the array's base type, take that element, and perhaps do some additional processing. In this case, we're taking the element and adding that to an accumulator. And then we simply, outside the loop, report what the total findings were. So the array contains 5 elements. That's our message here. And then we walk through the array using our for each loop. And notice we get all 5 values that we know to be in the array. Those were obtained simply by making a reference to this variable here. This is the value that is going to receive the selected object for the current iteration through the loop. And then in the second part, we simply dump the total. That was from the second loop that we had, where all we did was take the element, whatever its value was, add it to our running accumulator, and then simply report our findings. That's the basic idea of the for each loop, this kind of enhanced version of the for loop. So the simplification here for the programmer is they don't get bogged down or distracted by the use of the subscript or the index. So the general statement would be, if you don't need to access the index itself within the processing of the loop, then this is a great way to process all of the elements within the array. So this summarizes our processing that we just talked about, and the point here is the variable that we use has the same type as the elements in the array, the base type. The variable is declared within the for each loop. That's where we announce it, and it then gets used there as a local variable. We use a colon after we declare the variable, and then associate that with the name of the array from which we're going to extract the elements. So it's a little different than when we declare variables in some other structure. We terminate with a semicolon. Here we terminate, not so much a terminator as it is a separator, but we follow the declaration with a colon. And the important point that we observe here is there is no mention or reference whatsoever to the subscript or the index. That may come into play internally in processing, but we never see it. We never have to interact with it. So if we compare a couple of ways of writing loops, we can use the for each loop as shown in our first example. Then our second example right below it accomplishes the same result, but using the traditional or conventional for loop where the index or subscript comes into play. I would say pause for a moment, look at this, and make sure it's clear to you. The third example that's shown here says that this one relies upon the subscript or index as part of the processing within the body. It's actually looking at what the value of that index is and using it some way in the processing of the body. Therefore, this loop could not be altered and run using the for each syntax. So if you do not need to access the array or subscript, then the for each loop might be very appealing to you. Another point to consider with arrays is that when we declare an array is instantiated effectively at runtime because an array is an object. This yields a great deal of flexibility to us. So for example, we could ask the user to enter a value that says the number of elements that they wish to have within the array. So that is determined at runtime, not at compile time. Then we take the response of the user and we use that when we invoke the new operator to bring the array into existence. This is a possibility for us because an array is an object in Java, and the object is instantiated at runtime. So if the user responds with a value of 10, an array with 10 elements will be created. If a user responds with a value of 100, an array with 100 elements will be instantiated or created. This makes it much more robust or dynamic. It's very flexible. And that is attributable to the fact that the array is an object. Actually quite neat, quite beneficial to us. Another consideration we have with arrays is arrays don't always have to be filled. So if we create an array that can hold 10 elements, we may not always fill the 10 elements. For example, in some situations, we may have a number that is smaller than that. Maybe we have only 8 values. We anticipated that we would need 10, so we allocated 10 for the array, but only needed 8 when we actually ran through the processing. Therefore, we have an array that is not completely filled. I refer to that here as a partially filled array. The examples we've demonstrated thus far in accessing the elements of the array accessed all of the elements. But in this situation, if we have 10 elements, but only 8 of them contain significant or real values, we don't want to access all 10, only the 8 that contain the real values. This means that an additional step has to be taken by the programmer. The programmer has to create another variable that keeps track of the number of elements that actually contain real or legitimate or valid values, and use that variable to control the number of iterations through the loop. So in order to do this, we might create a variable that we might call count, and in the logic of the program, assign a value of 1 to count when we've processed 1 element. And then for each subsequent element, we add to that value. So if we process a second element, count becomes 2, a third element, count becomes 3. And at the end, the number of elements that we've actually processed will be reflected in count, which in the case of a partially filled array would be a smaller value than the length of the array. So then in subsequent processing, we would not go up to length minus 1, but we would go up to count minus 1, the actual number of populated elements. This is a very important concept to grasp because this is going to be used a great deal in the real world. You allocate the size of the array or the number of elements in the array for kind of the worst case situation where this is the maximum number of elements you anticipate, but you don't always have that number of elements to deal with. So you have to manually keep track of the number of elements and then deal with what you have, a partially filled array. So what is it that we've addressed in this video? We've covered the concept of accessing elements in the array using a loop, where the idea is we're going from the beginning of the array, the first element, index 0, up to the last element. We also talked about an alternative way of declaring the array where we initialize the values at the time it's created by supplying those values in what is referred to as an initialization list. Then we talked about array bounds being checked at runtime when a Java application runs, and that lowest or first subscript is always 0. The highest or last subscript would be, say, the length of the array minus 1 if the array is completely full. We talked about this enhanced for loop processing, the for each loop, which is very useful for reducing the complexity of the code and makes no reference whatsoever to the index or subscript of the array. And then finally, we wrapped up with partially filled arrays, where we may have a number that is smaller than the actual length of the array, such that we have fewer than the number of slots in the full array that are actually populated. The examples we provided are available on the accompanying website, www.timhartley.com, and we encourage you to take a look at those and try those out on your own. If you enjoyed the video or found it useful or informative, give us a thumbs up, offer any comments you might have regarding the video, and once again, consider subscribing to the channel to be informed of the posting of future videos. And finally, thanks again for watching.